Mayank sir has completed his PhD from IIT Bombay. He is among the first recipient of Indian section of American TR35 award, first Indian to receive IEEE EDS Early Career Award. Sir has numerous such awards like NASI Award, high reputed awards like National Academy of Science Young Scientist Platinum Award, INAE Award, DIT Young Faculty Fellowship. Sir has more than 150 peer-reviewed international publications. Sir also has got 47 patents so far. Sir has worked with Infineon Technologies Munich. Sir has also worked with Intel as staff engineer and senior engineer. He is right now associate professor at IISc Bangalore. Currently, his research focus is on nanoscale beyond silicon CMOS for SoC applications. Other area of interest right now from his work group are physics of semiconductor devices for their reliability, electrothermal interaction, thermal transport. So we are really fortunate that you have accepted our invitation to deliver the session. Sir, I request you to initiate the session.
Thank you, Professor Soni, for this introduction, and also I'm thankful to the organizers for having me here. It's always a pleasure to interact with the students and faculties and educate them about new things, futuristic things. I hope I can meet the purpose once again. Let me share my screen quickly. Okay, can you confirm if you can?
Yes, the screen is visible, sir.
Okay, thank you very much. Okay. I believe the session has faculties as well as students of your institute and university. I have oriented this.
Excuse me, sir. The program has faculties as well as research scholars as well as postgraduate students. They are spread among the nation. We have 89 participants registered. Yes, sir.
Okay. I cannot see the screen, but can you tell me how many have joined this session, this particular session?
So roughly 40 participants have joined right now.
Okay, and they are from the same background as you explained.
Yes, sir. Yes, sir.
Okay, thank you. So, yeah, I have oriented this talk for a broad audience like this. I've been giving this talk at different forums since last several years, trying to educate people and share information about what's happening now and what's going to be the future. And that's why you see the title of the talk as the future of electronics or microelectronics and possible roles India can play. And in this particular case, particularly in the nanotechnology area for mobile systems, or when I say mobile systems, we are not just talking about cell phones, but mobile systems means anything which is mobile, anything which is handheld, anything which is miniaturized per se, right? So actually, we are talking about things which are miniaturized, and so miniaturized electronics and the possible roles India can play. The talk has been oriented or divided into following um, four segments. The first one is what I call advanced silicon CMOS or CMOS SoC. This is something which is happening now, and I'll talk about this. Then I'll talk about what's going to happen beyond the silicon kind of a nodes. I'll give you a glimpse of let's say how the conventional computing may get changed by neuron-based computing, and how the neural hardwares could be seen, and what kind of neural hardwares would be seen in future. Then I'll switch gear and I'll talk about, for instance, everything up to this point is all about miniaturization of things which process information or data for computing. And then I will switch gears for and talk about things which basically process power. Even there, a lot of miniaturization happens. Handheld systems are developed. And finally, I'll talk about an integration of the two schemes. What is you can call nano, and the other scheme is the power. Okay, so a curious question or observation. Um, Nobody in this room would have seen possibly this kind of IBM calculator, which is 60 years old. But if you just do a quick Google search and search for the initial days computers, right, you will find these kind of pictures. I remember visiting one such system in the museum in Munich, a very giant, massive IBM computer, which was developed even before the semiconductor era started, right? All vacuum tube stuff. Even this is pretty much close to vacuum tube and discretes, semiconductor discretes, right? Now, if you see this calculator, which could do basic operations like the kind of calculator which a tiny calculator can do today, during those years you would need something which is possibly of the size of my office, and just could or would be able to do again those simple basic calculations, right? So that was the size and scale at that time. In 60 years down the line, we have these extremely handheld, tiny mobile and handheld and these kind of gadgets, cell phones or laptops and tablets and whatnot. They are less than a kilogram. They are pretty sleek, and they can do possibly billion times more computing operations than what this IBM calculator can do. So now we have something which is possibly several hundred times or several tens of million times to billion times more capable in terms of the kind of compute these systems can do. Obvious question comes is how this is possible, right? So if we go back, date all of this back, the basic building block of all these systems is a semiconducting chip. But that is what we see today, right? In principle, a semiconducting chip is nothing but millions and billions of transistors integrated together, which means the basic building block of all of this is not even chips, it's actually a transistor, right? Something like this. So before the semiconducting transistors, everything was vacuum tube, right? These devices, as I'll show you next, were of the size of 1 centimeter, right? And now we are talking about in less than a centimeter, cross centimeter, we are talking about integrating more than several million transistors, right? We are talking about integrating in 1 cross 1 centimeter. We are talking about integrating a billion transistors, right? So something certainly happened drastic and significant in the field that we are able to achieve this kind of milestone. Right? So if you see how the technology evolved, or how the basic building block technology evolved, which is the transistor, right? In those days, it was all vacuum tube. The vacuum tubes, as I said, were of the size of more than a centimeter. Then came the transistor, right? So everything was discrete. Still, these transistors, though they were much more reliable, compact, but they were not as compact as the kind of transistor that we see on chip today. Right? So even if you, I don't know how many of you would have opened a television set, let's say from 20 years back. I mean, I'm talking about the television sets from the CRT tube kind of a time. If you have opened that television set, I was in a school at that time, you see that everything was discrete. The best chips that you get on the television units, where in the best case would be a very basic microcontroller and otherwise just some gate logics. Otherwise, anything which was analog was all discrete. There was no analog integrated. The digital was also pretty much on board, and the chips were nothing but the gate logics. So you basically have these gates inside certain ICs, and you integrate them together to achieve certain kind of digital logic on board. But still, everything pretty much discrete, right? So of course, if you make these transistors and integrate these kind of transistors in hundreds and thousands and millions in numbers on board, you are going to have a very bulky electronic, very bulky system. That's why on those days, the electronics were quite bulky. Even the radios, if you remember, if you have seen the radios from that time, the radios itself were a lot bulkier than the kind of television sets that we have today, right? And that was all because of this kind of bulky discrete electronics. But then, of course, things advanced. One of the Nobel Prize in physics was also given for that. Things advanced in terms of integrating things together, right? Integrating these transistors on a single platform. So like earlier we had on one silicon chip, one transistor, which is a discrete package. Now you have more number of transistors and ways to interconnect them on a single silicon chip, which is called the large scale integration or something. Now, as the large scale integration technology advanced, we were able to integrate more and more number of chips or more and more number of transistors on the same chip. And that's how things progressed. And gradually, people started seeing millions of transistors integrated, then billions of transistors integrated. And today we can see chips which have more than 5 billion transistors and multiple cores integrated inside the same package, right? So this is, if we zoom into what happened in last 10 years, this is what you notice. What you notice is that 10 years back, let's say around 12 years back, the technology was at a scale which was called 45 nanometers. Now, 10 years down the line, the technology today is less than 5 nanometers, right? So now even there are 2 nanometer demonstrations done. What is going to happen in future? That is something not clear. So in the first module, I'll talk about this part, which is the advanced silicon CMOS. And the next module, which is the graphene and 2D material part, I'll talk about this part as in replacement of silicon or beyond silicon kind of technologies. So let's see what it enabled, right? What you see around you are these smart gadgets. You see cell phones, you see tablets, you see laptops, right? You see these tablets, cell phones, laptops, right? You see many new kind of gadgets which were not available in the older times. The other segment which this kind of advancement, the chip advancement has done is the CPU and the data center segment. For instance, now you have these, if you buy a desktop computer, the desktop computers are pretty advanced, right? These servers, all the processing units available at the cloud, they are pretty advanced, right? I mean, now you can simulate things which were practically impossible to simulate or compute in the older times. So this is the kind of advancement that this the chip technology or the nanoelectronic or microelectronic technology has led to, that you are able to do things which were not possible in the older times. Now let's see what goes inside a chip, right? If you build a chip, and particularly I'm talking about system on chips. So as I said, the handheld systems are possible because of what is called the system on chip. Whereas the data center, the PC clients, they were always there, of course, with lower performance, and they are the backbone of those systems are the computing unit, the CPU chips. The SoC has CPU inbuilt plus additional things. So let's see what goes inside a SoC, right? So of course the SoC will have a core, which is the memory and the logic part. This core is self-sufficient to build a CPU. But then, and when you're building a system on chip, then you need many other things. You need, I/O interfaces, all your interfaces like HDMI, USB, camera, whatnot. Everything requires an interface to interface with your core, right? So there are a range of interface approaches Some of them you are already aware of, USB and SIM card and HDMI and memory interface and whatnot, right? That's what you need to interface with the external world. Then you need different kind of modules which are not there in standard CPU. Like you need power management, you need battery management, you need all these reference generators, charge pumps, PLLs, right? Whatnot. They are not there in CPU, right? Then you need a lot of RF stuff inside SoC, right? You need a Wi-Fi, you need GSM, you need Bluetooth, you need GPS, you need other things as well. So into all these modules inside your chip, right? You also need then, since your SoC is going to operate at different voltages, you also need a lot of protection inside the chip, right? So let's see how things started. If you have seen, some of you would have seen the cell phones from year 2000, 2001, when the cell phones were just introduced in our country. These cell phones were quite bulky. And what best they can do was just make a call or send a text with 180 characters, nothing else. You cannot hear radio, you cannot play music, nothing else. Okay. So the reason was that at that time, what was present in form of SoC was nothing but the digital baseband and the analog baseband, right? So this is the capability it could offer, is just receiving and sending calls and making calls and receiving and sending text. Then gradually things started becoming a lot more compact. So for instance, RF trans receivers, which were earlier on a separate chip, also got integrated inside the same chip, and subsequently, the battery management unit, the power management unit across the chip got also integrated on the same chip. FM radios, and then even power amplifiers, which made the cell phones much more sleeker and lighter, and having a lot better range compared to what we had in the older times. Right, so this kind of integration happened as a function of time because of the maturity of the technology, and I'll talk about what is that maturity of the technology in terms of the capability of the devices available for designers to build these chips. But what it led to is, these kind of smartphones or smart systems or gadgets, which would have all kind of features inbuilt on the same device, right? I'm showing this picture, this particular picture. It's pretty old smartphone, but this is, I would say, among the first smartphones in the market, which came up with all kind of features and integration with a smartwatch. Now, where all of this will head to? All of this will head to highly interconnected world, highly autonomous world, where everything will be driven in a more autonomous sense. Everything would be connected to each other, right? So for instance, in this case, what you see is an example where you can centrally, using your tablet from a central location, you can operate things which are placed at a remote location. For instance, your consumer appliances or even your car can be driven through remote control operations or in a more autonomous way, and that is all enabled by the kind of SoCs that I was talking about. Going forward, it's predicted that every person is going to carry at least 5 devices, and all these devices are going to be connected with every person's other devices, right? So you can think of a highly interconnected world with every human carrying a lot of intelligent electronics, and a lot of things would be taken care by this intelligent electronics, right? And all of this would become possible because of the advancement in the semiconductor and the microelectronics technology and development of these SoC or system on chip. So I was talking about what kind of infrastructure you need for building SoCs. So if you have to build a CPU, all you need is a switch, right? Because inside a CPU, what you have a memory and you have logic. Logic is nothing. You have an N-type switch, you have a P-type switch, right? So for building a CPU, and particularly the logic block, all you need is an N-type and a P-type switch. NMOS and PMOS, which is just a switch. You don't have to care about its RF performance and log performance and so on. You just have to care about its switching performance, which means high I-on by I-off, right? High subthresholds, better subthresholds, lower VT, high I-off, that's it. You don't have to care about other parasitics, RF performance, and so on and so forth. Now, if you have that device, that N-type and P-type switch, and you have memory, which is again designed by the same switches, you are aware of the SRAMs, right? You can build these CPUs pretty conveniently, and that's the reason why the CPUs you can even build by coding things and then burning it FPGA. And if it is working in FPGA, it's going to work on hardware as well. There's no complexity in terms of building. That's also the reason why the CPU comes faster in the market, right? I mean, every 18 month or 2 years or 2.5 year nowadays, you see a better CPU coming in the market because the design is kind of lot straightforward. I mean, a lot of stuff is basically automated, parameterized. You can do it at the RTL level. You can code the entire architecture, right? You can test it on FPGA. Whereas when it comes to building SoC, you need a lot more, right? You need devices which can offer you mixed signal kind of capability, RF and capability, analog capability. You need devices which are offering much lower leakage, right? You need devices which are operating at higher voltages because you have to deal with all these IOs, interfaces, and many other things which operate at higher voltage. You need a technology which offers you very high gate and metal density because you are going to integrate a lot of functionalities together, right? So if the gate density and the metal density is not good, you cannot integrate so well. If the leakage is not lower, on the lower side, you are going to lose a lot of static power. If you don't have devices to do RF mixed signal and log, you cannot build the other kind of modules other than digital. If you don't have high voltage devices, you cannot build the high voltage kind of stuff like IO interfaces and other power amplifiers on board and so on, right? Now, where's the challenge going forward? The challenge is what is going to happen beyond the current technology nodes. So there, of course, the directions are for nanosheets, nanosheet FETs, and tunnel FETs, right? These are some new threads emerging. If you are looking for problem statements, I would strongly suggest you to look for nanosheets. Recently, there is some literature which has emerged from industry on nanosheet transistors, right? Look for nanowires, nanosheets. Now these things are emerging from industry. Or from future point of view, look for tunnel FETs, but tunnel FETs, a lot of research happened. You have to think of how the technology will evolve and how what kind of tunnel FET architecture can be practically realized and can be realized without changing the technology significantly. I mean, industry will never adopt to a technology or to a design idea which requires them to change the entire fab tool, processing approach, everything thoroughly, right? They will adopt to something which is easy to adopt. Okay, so think along those directions if you want to work on tunnel FETs. And otherwise, nanosheets are something which are emerging. Think of working on nanosheets and these nanowires, but look for problems which are practical to industry. The other aspect is the integration, right? So how do you integrate more and more metal or metal interconnects on the same chip? And how do you introduce high voltage capability on the same chip? So these are the transistors we are talking about, 2 nanometers in channel lengths. Now, in this kind of technology, how do you make something which can handle high voltages? So you have to think of innovative ways by which they can handle high voltages, like these lateral LD MOSFETs, power MOSFETs, and all on chip kind of things, right? So that the industry tomorrow can also design these kind of SoCs with these ultra scaled technologies. At present, whatever is there, 5 nanometer, 7 nanometer, or even 11 nanometer, they are only for processor applications. The SoC has yet not happened. So we have been working on several threads on those lines. This is some work from my initial days in ISC. I thought of showing it to you, where we worked on certain tunnel FET architecture, and here the whole motivation was to basically come up with an architecture which is not too different than the FinFET technology. And if one has to switch from FinFET to tunnel FET, the tunnel FET architecture should also be something similar to FinFET, so that one doesn't need to change the technology significantly, right? Okay. Now, on the high voltage side, there are several challenges as you go down to these scales. For instance, the device would have early quasi-saturation. What is quasi-saturation? If you see the ID-VG characteristic from the textbook point of view, you are aware of only this part, right? You have this nice IV characteristic. But then if you increase gate voltage further, in case of power devices, high voltage devices, this is relevant. You see these saturating currents. And this saturating current is nothing but, your GM will drop like anything. The on resistance would be compromised, the GDS would be compromised, and the transistor would be no more a amplifying device, a transistor per se, right? So this has to be addressed in these technologies. Safe operating area means that you have a device, and if your device fails, right, let's say if I draw a boundary, and if your device fails after these points, then this region is your safe operating area, and all you have to do is you have to keep pushing this safe operating area for these high voltage kind of applications, so that you can squeeze more current and more voltage from the device. EST reliability and Hotkey reliability are other critical threats which are worth investigating in case you are looking for a problem area or a problem statement to work on. So as I said, we have been working on some of these threats. So on LDMOS devices, particularly going all the way down to FinFET technology, we have done a lot of work, and certain things we did for Intel transferred this technology, and now Intel is kind of realizing all of this. Okay, so some power amplifiers we also demonstrated collaboration with Intel, and some high voltage FinFET devices were also demonstrated. Okay, so this was about the thread on the silicon CMOS and SOCs. Now, so let's say if the silicon is done, and at some point the silicon saturates, right? The performance saturates, and you have to keep improving. If you have to keep improving, what next, right? So that's where comes these other newer materials, where you have graphene and other 2D materials and 2D semiconductors. If we talk about graphene is nothing but a one atom thick sheet of carbon lattice or carbon atoms, where each carbon atom is connected in a honeycomb lattice fashion with 3 other carbon atoms. In plane, you have you have sigma bond, and out plane you have pi bond. The sigma bond is responsible for the mechanical properties and thermal properties, and the pi bond is responsible for the electrical properties. Now, if you roll this as depicted here, what you get is a carbon nanotube. Now, carbon nanotube has been very difficult to handle, but if it is graphene, it's easy to handle compared to carbon nanotube. It's more predictable, and therefore a lot of work happened on graphene. In fact, carbon nanotubes were discovered a lot before than graphene, but people have done a lot of work on graphene because of the simplicity of the material and the unique possibilities. Okay, so what are these possibilities? Graphene, for instance, offers very high electron mobility. All of you know that the electron mobility or the mobility, carrier mobility, is the parameter which defines how fast the transistor would be, how fast the device would be, how fast the carriers will move, drift across the material. That's the reason why the theoretical cutoff frequency is 20 terahertz, but nobody has touched that limit yet, right? Graphene also offers very high thermal conductivity. That's because of the in-plane sigma bonds, right? And because of this high thermal conductivity, you can use it for applications where either you want heat spreading or you don't want any intrinsic heating across the device. Now, if you compare graphene's properties with the copper's properties, copper is the favorite material or the metal used inside interconnects. And if you compare graphene versus copper, you find that most of the properties that graphene offer are far more superior than what copper can offer, right? For instance, the current density, maximum current which copper can handle is lower than graphene can handle. Melting point, right? Tensile strength. Graphene is a lot more strong than copper, and other points. And that's the reason why graphene was considered to be wonder material, but the technology is something which is very tricky to handle. Now, I talked about terahertz, and what is that terahertz? Terahertz is the gap which is between the microwave and the infrared, right? It's the gap between these two frequencies, and this is interesting frequency band because for 2 reasons. One is the terahertz radiation is invisible, intrinsically safe, and non-destructive and non-invasive, which means it can penetrate fabric plastics, but will not penetrate skin. If you talk about the radiation, several materials like explosives, plastic explosives, have unique spectral fingerprint in this terahertz range. Okay, which means what can we do? We can, for instance, use it for homeland security. You can use it for imaging with non-invasive spectral identification, right? So you can use it for imaging or doing uncover concealed weapons on a person remotely without telling the person. A picture. This picture depicts all of this. You can also use it for spectroscopy, right? If you on the airport, if you expect or suspect that there's some dangerous non-metallic substance or plastic explosive, you can basically use this for developing scanners, and every material pass through that scanner, and anything which has that spectral fingerprint will be detected. Okay, the other application is the communication application, right? So for instance, you can use it for high altitude communications, micro nano airborne systems like these, right? Where it will be extremely lightweight, that you can put it on these kind of lightweight airborne systems, right? You can use it for wire-free large-scale systems, wireless interfaces, on-chip interconnect-free communications, and so on. Now, that is all fine, but what is missing? What is missing is the technology for electronics to control and manipulate the terahertz radiation for these kind of applications like imaging, sensing, and communication. Okay, worldwide there has been several programs, and we have been running a similar program in ISC as well. So under this program, we worked on several problem statements as far as the graphene technology is concerned. We solved many problems, and we could demonstrate record high performing graphene transistors. So in this case, for instance, the red curve is the graphene transistor which was demonstrated by IBM TJ Watson lab, right? And the blue one is the graphene transistor that we demonstrated, and this is better than the IBM TJ Watson graphene transistor. Now, another interesting thing is that the material they used is an expensive class of material. This is supposed to give the best performance, but it's an expensive class of material and not easily available. The material that we used is the cheap class of material, just CVD graphene. And despite the cheap class of material and lower quality material, because of the engineerings that we did at the device level, we could demonstrate much better performance. Same we did with the contact resistance. We demonstrated record low contact resistance for graphene, which by solving certain fundamental problems which were not solved before. Now, graphene can also be used for other applications. Graphene can be used for heat spreading applications, right? So for instance, as I said, the graphene has very high thermal conductivity or heat spreading ability. You can use graphene for heat spreaders. If you open a laptop, if you open a cell phone, what you find is you will find a thick graphite sheet. Now that graphite sheet is used to spread the heat away from the hot regions. If you open the laptop, you'll find that there are certain regions which are extremely hot. Now you cannot allow some regions to be extremely hot. So what is done is that you put these heat spreaders. They're not coolants, they're heat spreaders. They will spread the heat to the entire system. And that's why the entire system looks a little hot, rather few small regions being extremely hot. Then of course the heat is taken out through the vent and the heat sinks and so on, right? So the graphite is bulky and expensive. Now if you replace that with graphene films, which are cheaper and extremely lightweight, that you won't even sense the weight, right? That's one application. The other application is graphene is also, it can also shield EMI radiation. So EMI is something which is basically produced during fast transients and whatnot, and EMI can always kill either neighboring electronics or its own electronics, and therefore EMI has to be shielded. Now, EMI shielding is typically done in the current systems through metallic enclosures and certain EMI filters and so on. Now, you can avoid all those metallic enclosures if you change that with graphene-based EMI shielding enclosures. The metallic enclosures add a significant weight and size to the system, whereas graphene enclosures would not add any weight or size to the system because of their massless nature, right? They're one atom thick. Graphene is also transparent to light. So what happens is when you build displays, in displays you have the glass, you have certain semiconductor which is giving you the light, and then you have electrodes. The electrode is not transparent, right? Now, since graphene can also be used for for metallic applications as electrode, for instance, and graphene is transparent to light, you can think of building transparent displays by building transparent electrodes, right? And then there are other applications as well. For instance, you can build tunable antennas, superinductors, supercapacitors, terahertz detectors, terahertz sources, and whatnot, right? So graphene has many other applications as well. Okay, now this was graphene, but there's another class of material which is, or there are several other materials which also fall into this 2D material category. So what are these materials? So it all started with graphene. First, the graphene was discovered in its thermodynamically stable form, and then subsequently many materials got discovered in the two-dimensional form. Now, there are actually 700 materials which are available, but we can talk about some of these key materials which have promising properties for replacing silicon or basically building newer kind of systems, right? So these are basically sulfides and selenides of tungsten and moly, and then you have hexagonal boron nitride, which is an insulator. These sulfides and selenides of tungsten and moly are semiconductors. Graphene is a semi-metal as well as a metal, right? So with the combination of all of this, you can build whatever you want, right? That's why they're also called material on demand. Now, if you look into the properties, depending on which material we are dealing with, they offer different range of electrical, optical properties. And that's the reason why, they are even more interesting, because now you can think of fine-tuning the specifications, fine-tuning the outcome of the devices, the system that you're developing. For instance, you want to build optoelectronic devices for different wavelength range. You can choose a given material which can offer that particular wavelength. In the conventional bulk semiconductors, you had very limited options, but now with the 2D material, you have a lot of options that you can play around with the entire spectrum that is of your interest. Now, what all of this can enable, right? You can think of flexible electronics, right? So flexible cell phones, flexible systems tomorrow. You can think of television sets or these other electronic gadgets which are foldable in nature, right? You can think of these solar cells which you can roll and open anywhere and paste it on top of windows and rooftops and whatnot, right? You can think of these lab on chip tattoos, right? So you can basically have these electronics done on the entire 2D platform with all these electrodes, again made with 2D platform, and then you can make these lab on chip tattoos, and then you can integrate on skin, right? You can develop these lightweight micro air vehicles, right? Because these 2D materials are extremely lightweight. You can actually integrate the electronics on these micro airborne vehicles, which would not cost any additional weight over and above the mechanical weight of the system. So there are many other applications. If I summarize, you can also build flexible electronics with it, right? Wearable electronics, wearable technology with it, right? So if you summarize, there are many applications which you can deal with. You have computation, you have displays, you have energy storage generation, you have e-textile, you have you have healthcare, right? And given this region, worldwide there are several programs running on flexible and other 2D material kind of stuff, right? And keeping that in mind, keeping the promise, we have also been working on 2D materials in ISC since several years now, and we have solved several fundamental problems. For instance, one of the fundamental problem was how to make contacts with 2D materials and how to reduce the contact resistance. What we have shown is by doing certain quantum chemistry in the contact region, we could significantly reduce on the contact resistance, but also significantly improve the transistor performance. And now the performance is to an extent that one can even think of scaling it up and building circuits around it. Right. The other problem was that for building these CMOS systems, you need both NMOS and PMOS. Now, NMOS is something which everyone could do, but PMOS is something which people could not. Right. So we could find a way by which one can also make the P-channel transistors. So now we have high-performing N-channel transistor and P-channel transistor. And if you integrate these two, you build these high-performing CMOS systems, right? And we translated everything to CVD. CVD is the large area material, so we translated everything to CVD and demonstrated that all this scheme works for CVD as well. And as a function of all of that, we demonstrated significant improvement in all performance parameters, resulting into a technology which could be scaled up for building circuits around it, right? So if we have that, what one can enable? One can enable, of course, beyond silicon electronics, one can enable neuromorphic and computing, quantum computing systems. One can enable the optoelectronic and quantum detectors, but there are other applications as well which one can enable out of this, right? On circuit front, a lot of progress has happened. In fact, one of the demonstration was demonstrating a microprocessor with 2D materials, right? Then, of course, a lot of demonstration happened on the optoelectronic front. Right. So before I move on, I would request everyone to mute their microphones.
Premanand sir, kindly mute your microphone.
Okay, thank you. Okay, so let's move on. So now I want to give you some future visualizations, right? So I talked about what's happening now, right? Then I told you what will happen in next 10 years. Now I want to tell you what will happen in next 10 to 15 or 20 years, right? So now imagine that, think that can we mimic brain, right? Imagine a three-dimensional flexible chip which works like a brain. So you have something which is flexible in nature, three-dimensional nature, and also it works like human brain, right? What is the application? The application is enormous. There are many things that the conventional computer cannot solve. You cannot have artificial vision using conventional computers. You cannot have artificial audition, right? Or sensing with conventional computers, right? Those conventional computers, if you try to basically use it for these kind of high order sensory functions, they are constrained with power and speed, and they can never give you that kind of impression in real time. Artificial vision or audition or multi-sensory function or artificial tongue, all these things require processing in real time. You cannot wait, you cannot delay, right? Our human brain processes everything in real time. It doesn't wait, right? There's no compute time per se, right? So similarly, if you have high dimensional noisy sensory data, right, which you have to process in the real time, the order of magnitude, power and the computational strength needed if you use a conventional architecture is significant, and therefore you have to switch to neuron kind of architectures, the way human brain process all of this, right? There are other applications as well, like sensor networks, self-driving automobiles, robots, public safety, medical imaging, and whatnot, right? I mean, of course, all of this, if this happens, this is going to happen, let's say in 10 years, right? I would say this is 15 years, and this kind of stuff will take another 20 to 25 years. Okay. Now, of course, what you see a lot of, you would have heard of a lot of AI being discussed and neuromorphic stuff being discussed. That's all software, but software-based AI still is limited by the computational capability of the hardware that you're using. And the hardware that you're using is still conventional computer, is still von Neumann architecture. It's not neuromorphic architecture, right? So therefore, if you have to do a real-time neuromorphic processing, you have to switch to a hardware kind of a configuration. Now, how is that hardware possible? If you look into neurons, right, and if you derive a mathematical model of a neuron, what do you have? You have basically these summers, these integrators. Then you have some kind of a unit which basically, threshold unit, which basically gives you a high as soon as the threshold is crossed, right? And then you have these weighting functions, right? These weights. All of this can be very easily implemented with Cmos VLSI principles, right? So hardware neuromorphic system is possible, but the biggest challenge is actually in terms of this weight. The way the learning happens is very tricky, and the way learning happens is that these weights are adjusted. And in real neuromorphic systems, or in real human brain, what you have is the complexity is the biggest challenge. For instance, you have 100 billion neurons, and each neuron, so here this part is the neuron, right? This part is the neuron. So and what you see here is connected to, in this picture, it's connected to 3 neurons, but in reality each neuron is connected to some 1,000 neurons, right? Sorry, 10,000 neurons. So 100 billion neurons, each connected to 10,000 neurons, result into 1,000 trillion synaptic connections, right? So this, what you have, this W1, W2, W, the N, this N would be 1 trillion, right? So which means you're talking about a trillion, 1,000 terabyte, right? Kind of a memory. That's the kind of memory and the scale you need to process things like human brain, right? In a neuromorphic architecture. Now, if you try to do that at a software level, now this will give you a real-time result. If you try to do that at a software level using the most advanced supercomputer available, right, with 82,944 processors, just to simulate 1 second of the brain activity, it took 40 minutes. So it's not real time, right? Whatever information your brain can simulate, process in 1 second, and it's not human brain, this was rat's brain, right? That this supercomputer took 40 minutes to simulate that much, right? That's the kind of complexity we are talking about, and that's the reason we are talking about switching to a neuromorphic architecture, not programming a neuromorphic architecture and solving it with a conventional computer, right? So again, I'll come back to this question. If we develop a technology which can address this scale, can we think of developing a brain like chip which is flexible and 3D like brain? I'll not elaborate that further. It's only a concept yet. It's which I patented some time back. Now from here, I'll switch gears. Let's talk about the wide bandgap power devices, right? So far, whatever I talked about, this is all nano scale. It was all about transistor miniaturization, right? Integration and transistor miniaturization. Now here in this case, I'm going to talk about miniaturization, but at the same time increasing power handling capability, right? So where do we need these power devices? If you think of consumer electronics, right? All consumer electronics require power management. Whether you have a car, you have a fridge, you have a television set, anything, everything requires, your computer, even this laptop, cell phone, everything requires power management. And the power management is done by either onboard power electronics or on-chip power electronics. And the core of this power electronics is the power semiconductor device or the power switch, right? So, I mean, the market is huge for just for the power electronic systems, close to $140 billion. And for power management ICs, blocks on board, right? So you have it inside cars, automotive, everything that you see around, you have these power management systems. And the core of all of that is this power device that you see here, right? This is the device which is discrete device. This is the device which is the core of this power electronics that we are talking about, right? Now, as I said, that the discrete technology, the discrete device market, just the device market is $16 to $17 billion. The power electronic market based on these discrete devices is around $134, $37 billion. The integrated market like this, right, or like this, right, is around $100 billion. So what are the applications? If the applications are divided as per the voltage segment, so let's say if you go to the lower voltage segment like 10 volt to 100 volt, you have all these PC servers, DC-DC converter, onboard chargers and so on. You go to higher 100 volt to 1000 volt. We are now talking about heavy electric vehicles, motor controls, drives, and so on. And as you go further up, we are talking about power transmission, traction, right, locomotive, factory automations, and so on. And of course, the current ratings also go up as you go to higher voltages, right? So there's this huge market. Just the power inverter market is around $64 billion. That was last year number, right? Now within this, the gallium nitride market is supposed to be around 6 billion in another 5 years. So this is the kind of value scale happens, right? We talked about, I talked about the device market. And then from there, you have this jump from device market to the systems market. So something which is $18 billion translates into a systems market, which is $134 billion. Now, the acceptability for these power devices is very different, right? compared to the nanoscale transistors, the MOSFETs that I was talking about. The acceptability here depends on what market is looking for. For instance, they are following parameters: time to market, power density, switching frequency, reliability, losses, and cost. Now, if you compare any new generation of a transistor with the old generation, what you expect is following. You expect the power density to improve, you expect the switching frequency to improve, you expect the reliability to improve, you expect the losses to go down, the cost to go down, and the time to market come down, right? Now, for all of this, if you compare the parameters involved, right, I'll not get into the details, but if you compare the parameters involved, right, what you see everywhere is all you need is better semiconductor, right? You need better design, you need reliable semiconductor, and you need reliable design. That's all what you need. So in nutshell, you can say that the semiconductor is the killer for these power electronic systems. If you have good semiconductor device, you have a good power electronic system. You have a better semiconductor device, you have a better power electronic system, right? So now, why this enhancement is needed, right? Let's look into this. So as you improve the switching frequency, and the switching frequency, as you know, is a function of how good or how fast the transistor is. As you improve the switching frequency, the size of this magnetics, right, and these passives will come down. So as it comes down, the chargers or these power electronic systems become smaller and smaller. How many of you, I mean, most of you would have noticed 10 years back, 15 years back, these laptop chargers or cell phone chargers were very bulky and not that fast. Nowadays, the laptop chargers are fast. You can charge your battery in just a couple of hours, and yet they are not as bulky as they were in the older time. So what does it mean? It means the power density has increased, right? The power capability has increased. They can pump in more current into the battery, which means they can charge faster. While pumping more current into the battery, they are still sleeker, lightweight, which means the power density has increased. The power density increased because the size of these magnetics and passives and everything came down as a function of time or as a function of the switching speed. Now, what happens is, every technology has a certain limiting point, and that's where it's stuck. So silicon cannot switch at, a frequency higher than a certain number. Beyond that, it's already saturated. And that's where gallium nitride comes into picture, because gallium nitride can offer the performance that silicon cannot offer. And that's the reason why it's projected that gallium nitride is going to replace silicon from 100 to 900 volt kind of a segment in another 5 years, right? So let's see why gallium nitride is so attractive. If you compare the properties, what are the properties that are most important or attractive for a power device? One is the voltage handling capability, and the second is how fast the device is. The voltage handling capability depends on the critical electric field. How much maximum field you can apply across the device before it breaks. So as you can see, gallium nitride has highest critical field, right? Which means it can handle much higher voltage than what silicon can handle. Now, if you see the mobility is the parameter which defines how fast the transistor can behave. The mobility is better than silicon, right? And certainly much better than silicon carbide. So this is also a reason why gallium nitride is better in terms of speed compared to silicon device, right? So it can handle higher voltage and still offer higher speed. And that's the reason why the on resistance versus breakdown voltage cutoff, or the trade-off, is better for GaN than silicon. What is this trade-off? If you see, for any given on resistance, silicon offers 10 times lower breakdown voltage than what GaN can offer. In other words, for any breakdown voltage, right? So for any breakdown voltage, GaN would offer much lower on resistance than what silicon can offer. So what you need for a power switch? In a power switch, right? If you see your circuit, you need this switch to handle higher, more voltage, and still the resistance through the device should be as low as possible to avoid conduction losses, right? So you need higher voltage and lower resistance. Now, there are other properties as well. For instance, the gallium nitride, just because of its properties, can be operated at higher junction temperature. Higher junction temperature means it requires lesser cooling, means lower heat sinks. The other thing is that it's a high electron mobility device, which means that there's no reverse recovery effect, which means the losses are negligible, which means again you require lesser cooling. Second is that you can actually go to higher switching frequency because there is no reverse recovery kind of a phenomena. Other is, since you can go to higher switching frequency, you actually require smaller magnetics and passives. So smaller magnetics and passives and smaller heat sink will help you making your system size and weight reduced. And that's the reason GaN is considered to be the wonder material for power electronic engineers. Right, so what it can enable? It can enable electric vehicles, traction, all the way other kind of applications in this 100 volt to 900 volt kind of segment. And why one has to do that? It's not just about weight or size. You are also improving efficiency. Improving efficiency is going to help you reducing cost and improving the design as a function of time. It's also going to reduce the cost of the overall system, right? So, and now if you improve efficiency, we are actually going to reduce the carbon footprint of your electronic device, right? The device is yet not fully commercialized. It's still capturing the market, and therefore there's great scope for this kind of thing in the country. There are several GaN programs across the world, and so we have one program here in ISC as well. The programs were heavily funded with the RDO, IT, DST, and more recently, this is now MITI. And more recently, MITI has funded us with a 300 crore gallium nitride fab. And that's what we are setting up now. Right. So I was talking about this power loss, just a simple calculation from 2014 that I did. If you just convert all the silicon electronics with GaN electronics and save the losses, you're going to save 2% of India's GDP kind of money that we are losing on power. Some examples from here, if you just replace silicon power MOSFETs with GaN power MOSFETs in tablets, cell phone, and laptops, you save 20%, 23% of the energy. Same kind of savings happens in the variable frequency device or data centers as well. In 2014, the amount of this saving just from these applications was more than the FDI that we received. So there are several startups in the GaN segment as well. If I can modify this plot, in 2020, we also came up with a startup, a Gan Manufacturing Startup, which is called Agnit Semiconductors Private Limited. The purpose of our startup is to develop this technology and commercialize it, manufacture and commercialize this technology in the country. Now, all of this was possible within the country because we solved many problems, right? What are these problems that we worked on? For instance, gallium nitride is normally on device, right? It's fundamentally an on device because the channel is always present, right? And that's the reason why the threshold voltage is always negative. But for power applications, for power electronic applications, you need a normally off device. You need an enhancement mode device, which means you need a threshold voltage which is greater than 0, something like this, right? Like a typical N MOSFET that you are aware of. So we had to convert this normally on device, fundamentally normally on device, into a fundamentally normally off device. That was a problem, that was a challenge that we addressed. And there are several reliability challenges with these kind of high power devices because they have to handle a lot of power, a lot of voltage and current. Right? So there are several reliability challenges we had to handle. And that's what we also worked on. Is there a question? If not, I request you to please mute. So, right. So I'll not get into the details of this. We had to build a lot of unique setups to explore many of these challenges, right? And probe phenomena, probe physics, and so on. Of course, we worked on various technology aspects of these devices, all the way from contacts to gate stack and field plate design and buffers and whatnot, right? And as a result of that, we could solve these problems. For instance, what you see here, you see, from normally on device, which is a negative threshold voltage, we were able to shift the threshold voltage, right? So for instance, in this case, you see devices with positive threshold voltage. And this is all repeatable. So you see, characteristic for, some several hundred devices measured and plotted together. just to prove that statistically they all are working as expected, right? And these are not outliers. The characteristics, as you can see, is as good as textbook characteristics, which we demonstrated a 600-volt 4-amp kind of transistor technology with performance on par with the best reported numbers in the literature for this kind of breakdown voltage. We also worked on a lot of reliability aspects in this technology. I will not get into the details, but understanding all of that helped us pushing the reliability. I was talking about the SOA, or safe operating area, earlier, and pushing the safe operating area to a higher window as a function of all the reliability studies that we did. Now, a derivative that we did of this GaN technology was a Gand diode. In any power electronic system, if you remember the circuit, you have a switch, right? This is connected to gate drive, and then you have a freewheeling diode. I'm just drawing something basic. It could be anything else, right? So you have a switch. This is your power transistor. You also need a diode, right? So we also developed these diodes, and as you can see, the characteristic, we could develop these 16 amp kind of diodes, fairly sharp and small cut-in voltages, right? And very high breakdown voltages. Okay, so this was about our achievements on GaN and where GaN is progressing. Let me now conclude by talking about the last module, which is nanoscale power SOC. Now, why nanoscale power SOCs? Right? Power SOCs are typically, these silicon power MOSFETs with these silicon DSPs and the silicon gate driver all on the same chip. Now, if you change this silicon power MOSFET with a GaN power MOSFET, what you do is you are saving, a lot of area. We are saving 60% of the area. Now, this 60% of the area saving is nothing but 60% of the cost saving. Now, where that cost saving will affect, for instance, if you look into the LED bulbs, if you open LED bulb, you will see these kind of small power electronic modules. If I change that with these kind of these ICs, power electronic ICs or power SOCs, I save a lot of money, right? Similarly, there are many other applications where these power electronic ICs or power management ICs are used, and these can be replaced by GaN-based power electronic ICs. And going forward, if you can adopt or use the advantage of all the 2D materials, for instance, you can have a GaN on silicon as the power MOSFET. As I said, a typical chip will have a power MOSFET, then a DSP controller, and then you have a silicon gate drive, right? So this part can still be done as GaN on silicon, which is here. Now this part and this part can be done with these MOS2 kind of a chip, the 2D material kind of a chip. And then I showed you in the circuit, you have these inductors and these capacitors. So these superinductors and supercapacitors can also be developed with graphene and CNT, and you can integrate that too on the same chip. I told you that graphene is also a very good heat spreader. So you can use graphene all around for heat spreading. And I also told you graphene is also very good for EMI shielding. So you can use graphene all around for shielding EMI from this kind of an integrated miniaturized power electronic chip. So on this note, I would conclude. I have talked about the future or next generation of electronics. I have talked about Cmos and how all of this is going to be converted eventually into flexible, wearable, two-dimensional kind of electronics beyond silicon electronics. Going further, you will also see these brain synapse-inspired chips. At the power front, I talked about wide bandgap semiconductors. All of this will translate eventually into integrated power electronics. And of course, all these newer materials will enable newer applications like terahertz and optoelectronics in unique wavelength frequency bands. As far as the industry is concerned, already sees this happening in 10 to 15 years. For instance, on 2D material, there's a big industry consortium working, right? There's a big market going to come up in next 10 years. In case of silicon, CMOS, and power, we kind of missed the bus. But when it comes to next generation electronics like graphene, GaN, 2D, they don't depend on the previous generation learnings or failure. And therefore, we can start afresh. It's a very different ball game because things are not dependent on silicon failures. It's disruptive technology, results into disruptive patents. The question I'm asking to all of you is, can we jump the roadmap and take a lead in next 10 years? Thank you very much. I'm open to your questions.
So we have received one question from Amit V. Patel. What is the unit cost for electricity generated from graphene-based cell?
There is no electricity generated using graphene. Graphene is not used for generating any electricity.
Dear participants, if you have other questions, feel free to ask. So I have one question from my side.
Yes, please.
Sir, in this run, you have a couple of times said that we have missed the bus. So, sir, where you see the the stand of the Indian government to make us ahead in this run?
Well, I have a different view. The government cannot do everything, and we cannot basically think of government doing everything. If you look into American history or European history or let's say even Asian history, Taiwan or other countries, it's never that the government has done everything or government has initiated. Right? Government never asked Tesla to invent something, or government never asked other people to invent something. Government never asked those industrialists to basically start from scratch and build industries. It was always done by people. Government, the job of government is to basically offer the ecosystem and be supportive, which I believe is not too bad in our country. We need to change our mindset. Now, what kind of mindset we need, right? Do we have risk taking ability, right? In our country, for instance, when you talk about startups, most of the startups are software startups. Most of the startups are not manufacturing startups. Most of the startups look for quick returns. Same with the majority of the people. Whatever we try to do, we look for quick returns. Manufacturing cannot give you quick returns, right? Uh, Manufacturing never gives quick returns. For manufacturing business, you have to be patient, right? The return on investment comes late. But anything which doesn't give quick return, and if you have to invest in that, it requires a lot of risk taking ability. The question we have to ask ourselves is, are we risk takers, as a country, as this population, are we risk takers, right? If we are not, then it will take ages. If we are, or if the new generation is capable of taking risk, yes, of course, this is going to change.
Yes, sir, very well explained. Sir, let me ask you one more thing. You have mentioned one of the startup from your side, that is Aganit. So can you tell a few things about that?
I would say that's a good example of risk taking ability. Though we raised money, we also invested a good sum from our pocket. We know that the return on this investment is not going to happen any soon, because developing these technologies itself takes 4 or 5 years. Maturing them for reliability, qualification, testing in systems, all of that is a long time scale, right? But we have done that. We have raised VC funding. We have invested our own money. We have got to a point where we can really do something and demonstrate something, and then go for the next round. Now, there, what we are trying to do is, we of course have a technology that ISC or we developed. Agnit has licensed all of that, and we are now trying to scale it up to a level where we can basically put these devices into real systems. Once that happens, of course, the next level of scaling up happens. Right. So on one hand, I shared this because I wanted to highlight that when you get into manufacturing, a lot of technology and engineering problems need to be solved. Um, it's not just software that you keep on fixing your code and it works. A lot of technology engineering problems need to be solved. On practice, it has to work. Repeatedly, it has to work. right? But it's not impossible to do. I mean, all you have to do is you have to take risk and get into that. There are always chances of failure, but if you don't do it, you will never know whether you are going to fail or succeed.
Definitely, sir. So Yogesh Tiwari, sir, one of our participants, has written, your work has motivated us for problem solving, innovative design and solution. Market capture, startups, patents really is a benchmark. Thank you for delivering such an amazing session. He's also asking that, is litho facility available at IISc Bangalore?
Yeah, of course. It's there.
So,
It's
sir,
there not only in ISC, it's there in IIT Bombay and a couple of other institutes as well.
so,
I
sir,
don't think the problem is with the facility in the country, the problem is with the ideas and the risk taking ability. The newer generation need to come up with better ideas and need to have the ability to take risk, rather looking for quick solutions or opportunities to settle down quickly. If you want to get into a startup, you will never be in a settling down mode.
sir, as per you, which will be the next device that will come into production after FinFET?
It's already in the news, right? It's going to be nano sheet fed.
Okay. Okay.
Participants, do we have any other questions to be asked? Okay, sir. If I sum up this last 1.5 hours of time, then we have seen the light on market perspective, technology perspective, economic aspect, material uses aspect in the semiconductor devices, biological aspects also we have seen, as we have seen the calculation related to the human and rat brains with the VLSI technology. That was quite interesting. So the overall, I can say that the talk was complete blend of width and depth in the current world and VLSI connections. So we are really fortunate to have you with us, and we have really liked your talk and the way you have solved all our queries. Thank you very much, sir.
Thank you. I thoroughly enjoyed this session, and I congratulate you for organizing this. And I
Thank you,
hope
sir.
your participants would have some take home,
Sure.
um, and some of them really come up and emerge as risk takers in future.
Yes, sir. Sure, sir. Thank you, sir. So, dear participants, as per the schedule given to you, tomorrow sharp at 9:30, we are going to start with the first session. Uh, wish you a good evening and enjoy your time.